been talking one curve, and then we added in two curves and how we would find the area between two curves, and that we would always take the top curve minus the bottom curve, and then we kind of looked at some variations of that when the top curve and the bottom curve maybe changed. And so we're going to kind of start there, is the idea that we have to be careful when we are setting these up, looking at those different things and adding in some other requirements or constraints on our area. Something like the following: find the area of the region in the first quadrant that is bounded by y equals the square root of x and the line y equals x minus 2. So if we consider what that graph would look like, first of all, we've got two functions going on. Y equals the square root of x. It looks something like that. We've got the line y equals x minus 2, which would look something like that. But instead of shading all the area between them, it does give us a little bit more to go off of. Also, it says we are only going to look at the area in the first quadrant. So as we consider quadrants 1, 2, 3, and 4, the area in the first quadrant actually kind of adds in another element to this where we have to be careful, because if we're going too quickly, it just kind of looks like the area between two curves, and we would do top minus bottom, right? So as we think about, first of all, where we would be integrating this from, obviously in the first quadrant, we're going to start at x equals 0, and we need to figure out where this ends, right, to figure out where we would stop integrating, which would be the intersection of those two equations, right? So as we look at the intersection of those two, got to be a little bit careful in this because it's only the positive square root. So we're going to see something show up here that would have involved our negative square root, but we'll look at that in just a second. But I would start by just squaring both sides. Again, because at the end of this, I want it to say x equals, right? Figure out where their point of intersection is. If I write this twice in FOIL, I would get x squared minus 4x plus 4. Get that equal to 0, solve for x. Put x minus 2, what do you mean? To solve a quadratic, we need it equal to 0. So I would subtract that x over. So I'm going to, yeah, I need it equal to 0 to solve this. So I would subtract that x over. It is still factorable, though. It does change our factors, but what are the factors of 4 that add up to negative 5? Negative 1 and negative 4. Okay, so analyzing those answers, we get an answer of x equals 1 and x equals 4. Now, the hard part about this is we are looking at a square root. So you actually only get the positive square root when we look at this. But if I plug x equals 1 into my green equation, which was this line right here, we actually get a value of negative 1, right? So that one actually would only be a point of intersection if we got the negative square root as well. Okay, so what we're looking at is our point of intersection is over here at 4 comma something. Well, specifically 4 comma 4 minus 2 is 2. So we would be integrating from 0 to 4. But we do, again, have to be careful because as we look at that area, yes, it is between two curves. But this area right here, look at what it goes to. It goes from our red line, which is our y square root of x, down to the x-axis. So this is actually just the area under your square root graph, right? Until we get to this point where the two sides of our shaded area are the square root and our green line. So it kind of changes. Again, it's by two different sections. If I had done square root of x minus the line, we would have included this part that is not shaded because it's not in the first quadrant. So we're going to have to look at breaking this up right here where we enter in our green line. Let me show that in a color that's going to show up a little bit better here. Breaking it into the part that is just under our square root graph in the first quadrant versus between our square root graph and the x minus 2 graph. Okay, so two intervals. We got to figure out what that x value is. So where is it that that line y equals x minus 2 would hit our x-axis? It's 0 at 2, right? So from 0 to 2, it's just the square root graph. And then from 2 to 4, it's the area between those two functions. So top minus bottom. Top would be the square root of x minus, and again, guys, remember when you're subtracting a binomial, you got to subtract the whole thing or distribute that negative through, right? Minus x minus 2. Yeah. Right. Yep. You could do that as well. Because if it's using your integral rules, you could take this here, and then those two would be the same thing. Yep. Okay. Other questions? Okay. Now, I see a lot of people typing on your calculators, and yes, we definitely could do this with our calculators, and you guys can continue doing that. I do want to remind us, this is actually one that would very easily be considered a non-calculator question. I can find the antiderivative of the square root of x, or x to the 1/2, right? A lot of times it's easier to think of it as raised to the fraction exponent. So for example, on this one, our antiderivative of x to the 1/2 would be x to the 3/2 with a 2/3 in front, right? 3/2 times 2/3 gives me that 1. Doing the same thing over here, we're looking at an x to the 1/2 minus x plus 2, so it's antiderivative. Same thing, a 2/3 x to the 3/2 minus 1/2 x squared plus 2x, evaluated from 2 to 4. So we absolutely could do this without a calculator, right? And make sure that we are continuing to practice these without a calculator. But I know that a lot of people are typing that in. So what do we get at the end of this?
I got 3.333.
3 1/3? Is that what you said? 3.3? Yeah. Okay. Any questions? Now, what I want to do is today introduce you to a new way of integrating that can actually kind of simplify a problem like this, where we had to take into account different regions of this because it kind of changed what was going on as we moved across the interval from 0 to 4. Okay? And we haven't looked at this yet, but you don't have to integrate with respect to x. We can integrate with respect to the other variable in this picture, and that would be with respect to y. So what does that look like? If we consider the exact same situation, so if we look at that exact same picture that we just had, okay, we've been totaling up area as we move through that shaded region from left to right. But we can total up area as we move through a shaded region from bottom to top as well, okay? But then I'm moving along my y-axis, so everything then has to become something in terms of y instead of in terms of x. So what would those look like? Well, if I were to rewrite this so I can call this in an equation as something x equals a y something, I would solve for x. And that would be the equation x equals y squared, right? So we would be looking at this line, x equals y squared. And if I were to solve this for x, we would add 2, and this would be the line x equals y plus 2. And we'd be looking at the area between those two curves just like we were, but going up the y-axis. So up the y-axis, as we look at this, the lowest that that shaded region goes is 0. What is the highest that that shaded region goes? 2, because we're looking at, again, our y values. So as I add area from 0 up to the top of our shaded region, which would be up at 2, and again, integral means adding all of the things in that area, right? So from 0 up to 2. Now here's where it becomes a little bit, again, trickier. Remember, we always did top function minus bottom function, and if you look at just a very basic one, that typically meant the one farther away from your axis to closer. Well, this way. Farther away from your x-axis, closer to your x-axis, because we're doing bottom to top. But if we're considering this our axis, this becomes your top function, this becomes your bottom function. So we would want to go right function minus left function when we go with respect to y. Okay, so as I enter these in, my right function is y plus 2 minus my left function, which would be y squared. And we will now do this with respect to y. Okay. We, again, can do this by hand, and this is a very nicely set up one to do by hand. So let's go ahead and just do this one antiderivative by hand. 1/2 y squared plus 2y minus 1/3 y to the third, evaluated from 0 to 2. Plug in 2, and then I'm going to plug in 0, but everything becomes 0, right? So this is all 0, so it'll be minus 0, which is nothing. 2 squared is 4, 1/2 of that is 2. 2 plus 2 is 4. 2 cubed is 8 times 1/3 is 8/3. So this would be 6. In terms of thirds would be 18/3. 10/3, is that the same thing we got last time? It is, isn't it? 3 and 1/3, 10/3, same thing. Okay. So you can see it doesn't matter, actually. We can go in terms, and was it a little bit easier to do in terms of y than with respect to x, because we didn't have to break it up, did we? It was one interval that whole time. And so this is a good example of maybe it would be easier on some problems to switch what variable we are integrating with respect to in order to simplify the problem. Questions? Kyan.
So if you have like a velocity versus time graph, and you integrate it with respect to x, you'd be finding the total change in position over a certain time, right?
With respect to time?
With respect to time, yeah.
Yes.
So if you did this and you integrated the other way, what would you be finding? Total time passed over a change in position?
No, you're still finding the same thing. Yeah, we're still finding the same thing.
Okay. So it finds the same thing?
It still finds that same area.
Okay.
You got it. Yep. Okay, so side by side, I want to just make sure that we are the subtle differences in how we fill in our integrals, especially when there are multiple functions to deal with. So if we are writing an integral with respect to x, a couple things. First of all, remember that the interval that you put here, your a to b, needs to be x values. And our x values go from left to right in our shaded region. That the function that we fill in here would be our top function minus the bottom function. And that whatever that is needs to be written in terms of x. So those equations would look something like y equals something, and that something is what we would fill in here, right? They have to be y equals equations, solved for y. And that obviously we would end this with dx to match whatever variable we are integrating with respect to. If we then switch it to respect to y, moving up our y-axis as we total our area, our interval is going to be y values, which needs to go from bottom to top or low to high, however you want to mark that from yourself, for our lowest value up to our highest value. And that if we were to have more than one function as we are doing that we would go the right function minus the left function. And that these functions right here need to be written with x solved for, or in terms of y. So it would say x equals some function with a y in it, and those would go here. And that we would say that we are integrating with respect to y. All right, so looking at a couple of these, and again, we're going to use a calculator for some of this. Next one, it says, find the area of the region enclosed by the graphs of y equals x cubed and x equals y squared minus 2. Now, the conversation we're about to have about how I type this into my calculator is also going to be an incredibly important conversation to have as we go look at this picture and when we start doing our integrating. First of all, this would be this equation in terms of x. So if we were integrating with respect to y, that one would be done. If we wanted this one in terms of x, I would have to solve for x by cube rooting and get x equals the cube root of y. Agreed? Okay. So now I kind of have up here my in terms of x, but what if I wanted it in terms of y, or to integrate dx with respect to x, I would need my equations to say y equals, and this is where this one gets tricky. When you go to graph this in your calculator will always be y equals, right? It's already in there for you, okay? Which means I need to solve this equation for y, and this is where it's going to catch us a little bit here. This actually ends up becoming two functions as we graph it in our calculator, because when I'm solving this, what do I have to do algebraically? Plus or minus, which is actually two separate pieces to that graph and two separate lines when I type it into my calculator. So I have to type in the positive square root of x and the negative square root of x. Just like when we talked about the equation of a circle. If I were to solve the equation of a circle into y equals, it would actually be two radicals, right? And the positive radical indicated the top half of the circle, and the negative radical indicated the bottom half of the circle. Okay, so let's look at our calculators. Go type those three equations that are written out as y equals into our calculator. Okay, so I've got my x cubed, I've got my positive square root of x, and my negative square root of x plus 2 in there. I set my window to like a 5x5 window to just kind of zoom in on the picture a little bit. It's kind of nice in my color calculator because you can see very easily the different graphs that we have on there. The blue is the x cubed. The red is the positive square root of x plus 2. And the negative, the black is the negative square root of x plus 2. Now together, those would have been the graph of the equation x equals y squared, right? And x equals y squared is a sideways parabola. But when we solve for y, it kind of becomes two pieces to that graph. All right. We will need at different points where these graphs intersect because the question was to find the area between them, right? So let's go ahead and find where those intersect using our calculators. I'm going to get this. So to find, and now let's talk about when you have multiple graphs in your picture, sometimes we have to be careful about how we're asking our calculator to find the intersection. So let's start with this intersection right over here between the blue and the red. So if I go to my second calc intersect and I move my bug closer to that, the problem is right now it's asking you your first curve, which I would consider the blue graph as my first curve because that's where my bug's on. I put it close to my point of intersection and I hit enter, and now you have to pay attention to which graph your bug jumped to. And my bug jumped to the red graph, okay, which is the two I want to intersect. So I hit enter again, enter to skip guess, and it'll tell me that those two intersect at this point. And then we would want to find where these intersect down here. But again, that's now the blue graph and the black graph. So I go to my second trace intersect. Bug is on my blue graph because that's your y. That's what I have typed in as y1. I get close to that point of intersection, but I want to show you guys what happens here. I'm close to that point of intersection, but when I hit enter, it jumps to my red graph because that's what's in y2 in my calculator. Okay, but I wanted to find the intersection between the blue and the black, so I just arrow down so it's actually on the black graph. So it's going to find the intersection between those two. Enter again to skip guess. And it tells me they intersect at -1, -1. Okay, so any questions when we've got now those multiple graphs in there, how I take care of finding that? Okay. So our job is to find the, let me use a different color here, the shaded region, which would be all of that. And I want to look at this as far as what if we went in with respect to x, or what if we went with respect to y? Okay, so let's start with our comfort zone. Let's go with respect to x. Okay, so if we were going to integrate with respect to x, we know that we're going to find the shaded region, find the farthest left to the farthest right that we are finding shaded region. Okay. Well, we didn't really talk about this, but what is the farthest left that it's shaded over here? Over at -2, right? So we're going to start our integrating at -2. And as I look at this part right here, as I fill in, I can see that that really is filling in area between two functions. And those functions specifically, if I kind of covered it up here, but are the equations y equals the square root of x plus 2, y equals negative square root of x plus 2, and this one was y equals x cubed, right? If we look at our different functions on there. So this part is from red to black graph. It would be between those two functions. Good? Yeah? Okay. And so it would continue to be between the red and the black function until that spot right there where now it flips between red and blue function. So this would be my dividing line, right? That's where I would stop that first integral of my area. Making sense so far? Okay. So that would start at -2 here and stop at my x value because we're moving from left to right, so at -1. Top function minus bottom function. So our top function being square root of x plus 2 minus bottom function negative square root of x plus 2. Question? Oh, okay. Good? So far? All making sense? Okay, and then we continue on with our shaded region. And so from here on, all I have is a top function of red, a bottom function of blue, and it's just the area between those, right? So I just need one more integral, because as I connect all of that area, it's just between red and blue. top function minus bottom function starts at -1, goes up to, and again, we're moving along our x-axis, so up to our x value of 1.214. Top function is still our square root of x plus 2. Bottom function becomes the blue, which is x cubed. It does. The subtraction takes care of it between the two. All right. Grab your calculators. Math 9 that for me. $4.215. Did I read that right? 4.215?
Yep.
Okay. Practice getting that in your calculators correctly. That is the correct answer. So if you did not get that, we might need to check what you typed in, make sure you got all the parentheses in the right place. All the, you have to use subtractions and negatives correctly in there. You can't make a subtraction a negative or a negative a subtraction. They're not interchangeable on your calculator. Okay. Okay, now add in our new topic today. What if we were to integrate that with respect to y instead of with respect to x? So I'm going to erase all this, except for I'm going to need you guys to remember that for me because I need those back. Okay, so we had intersection points of -1, -1, and 1.214, comma 1.793. Okay. Writing on here my equations, but this time writing my equations in terms of x equals. So here's what becomes weird about this. This represents this entire sideways parabola, doesn't it? So that becomes now one function, x equals y squared minus 2. We need a moment to absorb that. It is no longer, if I am looking at this in terms of x equals, we're going to integrate with respect to y, that is the graph of x equals y squared minus 2, the whole thing, where before it was like two separate graphs, right? And then our other one does not change, but it is in terms of x equals cube root of y. So we only have two functions this time. Okay, still the same area, but as I fill in that area, notice as I go to shade this, I am connecting the blue graph to the green graph this entire time, aren't I? All of that just connects blue graph to green graph. I don't ever like go to an axis or like go to a third graph or anything, right? So it is purely the area between the blue and the green. Moving bottom to top on this. If we integrate with respect to y, our shaded region on the y-axis starts down at -1. And it continues up until the top of this, which is, again, our y value of 1.793. And this is, again, going to be a new idea for us, but going right to left. So our rightmost function, if I were to put a dot in here, the function that is to the right of that dot is the rightmost function. Okay, and our rightmost function would be cube root of y minus our left function, and our left function would be y squared minus 2. We know that if we are subtracting a binomial, you either need to distribute that through or put that in parentheses. It will make a difference. And we are integrating with respect to y, so dy. Now, we know that that very much changes what's going on because we're integrating this direction. Our functions had to be x equals. when we wrote them, but your calculator, your variable button is just a variable. Okay, so you will still type all that in. We will write y, we will type x. Okay, so let's try it out on our calculator. Grab your calculator. This time we're going to integrate from -1 to 1.793. Of this, make sure you either distribute the negative or put parentheses, but all of those letters are just an x on your calculator. It's the same thing, isn't it? It's the same shaded region. It should be the same thing, right? So moral of the story is, does it matter if I integrate with respect to x or with respect to y? Not if I do it correctly, okay? So which one should I use? The one that is easier. And sometimes there will be one that is clearly easier, and sometimes there will not be, and then it's your choice. And typically, if they're like equal, we would probably go with respect to x because that's our comfort zone, you know? That's what we're used to. But sometimes there's going to be ones that's clearly easier, and then there's some that are going to be like nearly impossible to go the other way. So I want to kind of talk about this. This is actually the first 3 problems on your assignment. Okay? So I'm going to help you think through what we would integrate with respect to. On problem number 22, the 2 functions they hand you to find the area between are x equals y cubed and x equals y plus 2. If they hand you the functions like that, it's going to be easiest to integrate with respect to what? Y, right? With respect to y, because we have equations that say x equals, right? So our functions are already written in terms of y. I would integrate this with respect to y. Absolutely. Okay. The second one, we don't have anything solved for, but as you consider the solving process, would it be easier to make those equations say x equals or y equals? X equals, wouldn't it? Okay. And if it's easier to rewrite those as x equals, should we integrate with respect to x or y? Y. Y, right? Now, I do want to point out, could I solve those for y and integrate with respect to x? Yes. Now, think on this for a second. If you solve those for y, how many functions would you actually have in this problem? 4. That's a lot to keep track of, isn't it? And potentially a lot of different sections that we would have to break that up into, because if we've got 4 graphs, there's a good chance that your top and bottom graph are going to be switching a lot through that picture, right? Strongly suggest then picking to integrate with respect to y, because we would have 2 functions. Okay, on the 28, y equals 2 sine of x and y equals 2 sine of 2x. What would you integrate with respect to? Absolutely. Do you even want to start the process of solving those equations for x? Then why would we, right? I would absolutely integrate this with respect to x. So it's whatever your equation is solved for, that's what we're integrating with respect to. Now, it is, in my opinion, very similar to the idea of when we kind of flipped between taking derivatives and taking integrals. You have to slow down and be like, wait, am I adding an exponent or am I subtracting from my exponent? Well, it's the same idea here. Am I integrating from right to left? Where am I picking my numbers for my interval? And also, what's my top function, what's my bottom function versus what's my right function, what's my left function, and slowing down and saying which way should I be subtracting the functions that I'm integrating between? Yes?
So your top function, you're integrating with respect to y is the greatest x value.
The farthest right.
Farthest right.
Yep, farthest right is your top function, I guess.
How would you know on like 22? Because if you say it's like dependent on the graph, because like sometimes you want to rewrite just because the graph you need to.
You can graph that. You would graph y equals x cubed,
Yeah.
cubed root of x, I should say.
But like if you say we didn't know the graph, wouldn't you want to make sure that the graph looked like good first? If it was like something you didn't know what the graph looked like exactly.
Yeah, I don't think they would give us something that we can't visualize at all to figure out rights versus left or ups versus downs.
Yeah.
Either that or they'll give us a picture.
Okay.
I'm not going to make it impossible. You don't have to just go guessing. Rest of your assignment is out of the book.